Okay, Algebra 2, Unit 1, Lesson 5 is called Sequences are Functions. Okay, our learning goal today is I can define a sequence by using a recursive formula. So as you look here, the thing that probably strikes out is the word recursive formula. We've already kind of learned what a sequence is. It's just a list of numbers that follow a pattern. We don't know what the word recursive formula means, so we're going to learn about that today. All right, an arithmetic sequence we've already learned is sequence in which each term is the previous term plus a constant. So I'll give you a couple examples here. So say I go 3, 9, 15, 21, ... So we're going to add 6 to each term. So our common difference is 6, and it keeps on going. All right. You could also subtract. Here's example 1. Example 2, let's say I start out with 100. Let's say I go down 9. Oops, 2, sorry. Now you might say it said plus a constant. Well, really you could say plus -9. So that's how it ends up being a plus, even when it looks like you're subtracting. All right, a geometric sequence is a sequence in which each term is a constant times the previous term. Okay, so let's see here, example 1. Let's say I start out with 4. Let's say I times it by 3. So I'm going to get 12, 36, 108, ... 9 times 3. Now, your sequence will keep getting bigger and bigger and bigger if the number you're multiplying by is greater than 1. So since this value here, 3, is greater than 1, it gets bigger. Now let's say I times this by 1/10. Now it looks like you're dividing. Looks like you're dividing by 10, but you're really multiplying by 1/10. All right, so if your number here that you're multiplying by is less than 1, or really between 0 and 1, this 1/10 is between 0 and 1, it gets smaller. Okay, so there's a little review of what we've done. Now let's talk about recursive formula. This is new. You might want to pause the video and write this down. Recursive formula is a formula or definition that describes a sequence relating each term to the previous term. Okay. So important to understand this notation. AN would represent the nth term of the sequence. And then that would mean AN minus 1 would represent the term before the nth term. So I'm going to give you a sequence here. Let's just say this is, 10, 12, 14, 16, ... So if this is the first term, second term, third term, fourth term, let me give you an example here. A4 equals 16. That means that the fourth term is 16. So what would be the term before that? Well, it would be the third term. A3 equals 14. That means the third term is 14. So if you notice there, 4 and 3, the term before the previous term is always going to be 1 less. So if I want to know what the term is, okay, it's going to be the term before it, or the term before it would be the an minus 1, okay? That would come before that. Eventually you're going to get up to n minus 1, okay, and so forth, kind of like that. All right, so if you ever see a of n minus 1, that means the term before the nth term. All right, so here's our warm-up. Describe how to produce one step of the pattern from the previous step. So take a minute, pause the video, and analyze the pattern here. And let's see if we can come up with the next couple terms and then see if we can describe it. So it looks like we start with one dot, and then in step 2, we had 2 dots. Step 3, we had a row of 3 dots. Step 4, we had a row of 4 dots. Step 5, looks like we need to add a row of 5 dots right there, okay? Step 6 is going to be kind of the same thing. We had a row of 6 dots right there. Okay, so add a row of dots to the previous number of dots. And the row that we're going to add is going to be equal to the step number. Okay, so for example there, step 3, we added 3 dots. Step 4, I added 4 dots. And notice what I'm doing here is I'm taking the previous number of dots and I'm adding it to that. Okay, so you can see here, step 4, I kind of boxed them in there. I took the previous picture, which was step 3, I put them both in the box, and then I added the step number 4 there. Okay. If I wanted to go on to the 5th one, I take the previous number of dots and I put it right there, and then I add the step number to it. So if you look here, step 5, we had a row of 5 dots to whatever was the previous number. So if I wanted to write that out into function notation, we'll do that here in the next activity. All right, so part 2. Here's the visual pattern of dots. The number d of n of dots is a function of the step number n. What values make sense for n in this situation? What values don't make sense? So the values that make sense, here would be whole numbers, so basically, actually not even whole numbers include 0. Actually, I would probably say what we call natural numbers or the counting numbers. So 1, 2, 3, 4, 5, and so forth. You need positive whole numbers, okay? Maybe if I just said positive whole numbers. All right, what values don't make sense? So this would be my make sense right here. Actually, let's do it this way. Make sense, and then I highlighted this color. And then don't make sense. Come over here. Decimals, fractions, and negatives. Okay, why is that? It's because, well, you start with step 1, and then you go to step 2, you go to step 3, you go to step 4. Okay, right up here, the next one would be step 5. We're not going to have step 4.5. That wouldn't make any sense, okay? And we can't go negative because we won't have any dots left, okay? We can't have step 0, step -1. These don't make any sense. So and here's a couple examples, like 1.3, that would be no good. 1/2, that would be no good. -10, 0, and so forth. Things like that. All right, so let's complete the table. So you could just count the dots. So step 4 is going to have 10. Step 5, we know that we're going to add 5 because step 5, we're going to add a row of 5 dots to the previous picture, okay? That picture is going to go right there. So really, I'm going to add 5 to this. All right, so if you look at this picture here on this chart, step number, you're adding it. Step number, you add it. Step number was really, and I guess I can move this here. This was really the previous term, which was 6, plus the step number. And then this one's the previous term, which was 10, plus the step number. So if I want to find the nth term, I need to take the term before the nth term, which is a of n's the nth term, a of n minus 1 is the term before that. And then I need to add the step number to it, which is n. All right, so there's my recursive formula. Why is it recursive? Because we're using the previous step right there, okay? All right, so use the first 5 terms of each sequence to state if the sequence is arithmetic, geometric, or neither, and then define it recursively using function notation. All right, so we'll start with this first one here. Let's see here. So it looks like I'm going up 10 every time. So if I'm adding the same number, we're going to say this one is arithmetic. Okay. So it looks like to get from every term to the next term, you take the previous term. So the term before the nth term would be the a of n is nth term. The term before would be the a of n minus 1. And it looks like I just add 10 to the previous term. Okay. Now, if this is confusing you, I'll do a little scratch work up here. Let's just pick a random number. Let's see here. What's the third term? Third term is 50. Well, how did I get the third term? Well, what did I do? I took the term before it, 40, and then I added 10. Okay. So I took the previous term, which was the second term, which is 1 less than 3, and I added 10. That's what I did. Okay. Took the previous term, added the number 10 to it. Okay. And it would work for any of them, really. And so let's go to the fifth term. What's the fifth term? The fifth term is 70. Well, how'd you get to 70? Well, you took the previous term and you added 10. Okay. The fourth term was 60, so it was really 60 plus 10. That's how I got to the 70. All right. So let me erase some of that there. All right, let's go to number 2. It looks like we are multiplying times 1/2, 1.5, however you want to do it. So that would make it geometric. So to get the nth term, I need to take the term before it. I need to times it by 1/2 or 0.5. Next one looks like times 2. So we're going to call this geometric again. And what do I do? Well, if I want to find the nth term, you take the term before it, which is the a of n minus 1, and you times it by 2. Okay, now you could write it either way for these. You want to put the 2 in front. This would be acceptable either way, because when you multiply things, the order doesn't matter. It doesn't matter which number goes in front. So either one of those is fine. Same thing up here with the one I did in red. If you wanted to write it like 0.5 times a of n minus 1, that's fine too. Okay. Either way. All right. Let's go to number 4. A little tricky here. You might be a little bit weak in the fraction department, but remember the trick that we learned last lesson when we did the Excel sheets? We could always divide. We could take 1/2 divided by 1. And that's going to give me 1/2. And then I could take, whoops, then I could take 1/4 divide by 1/2, which would be, you can type in your calculator. I don't have one on me, so I'll just flip it. And that gives me 1/2 as well. If you get the same number over and over again, we know it's geometric. Okay, so you could divide all of those there. We're going to get 1/2. Okay, so we obviously know it's geometric. It's times 1/2 times 1/2. If I want to find the nth term, I take 1/2 times the term before the nth term, which is the n minus for 1 term, and there you go. Let's go on to the last one here. This one looks like it's -7. And again, if you're not sure, you could always subtract 13 minus 20. Always subtract the previous term. 6 minus 13. -1 minus 6. And you see you get the same. Here's the only tricky one, minus -1. That becomes a +1. Okay, so this is really going to still give you -7. So I missed that negative sign. But yeah, you could check it that way. That's what we learned in the last lesson. So this one would be arithmetic. So how do I find the nth term? Well, a of n is the nth term. I need to take the term before it. And I need to, you could say you add -7, or rather than put plus -7, I'd probably just say -7, like that. Okay. So there you go. Pretty simple. All right. So a little bit of review here. If you want to write any of this down, go for it. Pause the video as needed. So a sequence is just a list of numbers. Okay. They might have a pattern. Usually has a pattern, but doesn't, I guess, necessarily have to. All right, let's take a look here. Let's start with the arithmetic. All right, arithmetic sequence forms a linear function, and basically you add to each term the rate of change. So here's an example. So my rate of change here on this one is going to be 5, because you keep adding 5. So we look there, there's my rate of change. So here's the only tricky part, your recursive formula. So they're calling this sequence G, I guess. And G1, that means term 1 equals 2. Okay? Really important to understand this notation. G1 equals 2. That means term 1 equals 2. So this is term 1, this is term 2, term 3, term 4. We want to eventually get down to the nth term. Now before the nth term is the n minus 1 term. Now we're just going to fill in numbers there, put dots because we don't know what all those are. But here's my recursive formula. G of n equals 5 plus g of n minus 1. So you're basically adding 5 to the previous term. Now, here's something that we didn't do. It says n has to be greater than or equal to 2. And they also give us the first term. So maybe I should go back a little bit and maybe add that stuff on there too. So if I were to go back here, let's do this. My first term, I should probably give my first term for all of these, in all honesty. So my first term here is 30. Okay. And n has to be greater than or equal to 2 because we know the first term, all my terms after here would be 2, 3, 4, 5. It's just kind of saying that would go in that direction. We would not go negative and can't have decimals and things like that. So if I go to this one here, let's put our first term. Oops, let's stay in red. First term would be 80. So there's that. If I go over here, my first term is 1. If I go over here, first term would be 1. And then over here, first term is 20. I should probably include the first term. That way you know where you start. Okay, so we could technically start at 20 for that last one and then keep subtracting 7. I guess I kind of left that part out. I described the pattern, but I didn't tell us where to start at. So you really need 2 things. You need to describe the pattern and where you start. So if I went back actually to that last one, I might want to add here a 1 equals 1. Okay, maybe add that in there so that I know where the first step is. Okay. All right, so back to this. There's my recursive formula. I give the first step, and then I give the definition. So this is the part that's a little tricky. The nth term, this is the explicit formula, technically. So we haven't really done this yet. So I wouldn't worry about that right this second, but we'll get to that in the next couple lessons. So here's another one. We're going to go -4 every time. So if I were to write my formula, rate of change is -4. First term, K1, they use K for this one, is -9, which no, it's not. That should be an equals 9. That's not -9. I don't know why I came up with that. K1 equals 9. And then you take the previous term to find the nth term, that would be K of n minus 1. And then you add -4. Now you might have said, why didn't you just write it like this? That's fine too. I would take either one of those. Okay. Then this just means since we already know the first term, we're only going to plug in numbers greater than or equal to 2. Right? We're going to start at 2 for n. We're not going to find the 1.2 term. We're going to start at the second term. All right. And then the last thing here is the explicit formula, which again, it forms a linear function. We just haven't really gotten to that yet. Let's go over here. Let's take a look at a geometric. All right, geometric forms an exponential function, meaning that your function will look like this instead of a line. And linear functions in a straight line. So we're going to multiply. This happens when we multiply. Here's my example sequence. So I'm multiplying by 3. So my first term is 2. So if you look here, 2, there's my first term. And then we basically take find the nth term, we multiply previous term times 3. Okay? Times 3. Okay. And then n has got to be greater than or equal to 2, which it'll pretty much always be n is greater than or equal to 2 if you see that notation in the book. Okay? Here's the explicit formula. And what happens is, again, it forms that exponential function there, which we haven't really got to. So here's another one. You can see you're multiplying by 1/4. Okay. So here's my first term. First term. Right there is 160. And then you take the previous term. So to find h of n, we take the previous term and we times it by 1/4. Okay. All right. So goal, I can identify a geometric and arithmetic sequence recursively using function notation. I think so. You got to make sure you give the first term, which I forgot to do actually, but I remembered before the end of it. And then you got to give the pattern, what you do to the previous term. All right, so here we go. Use the first 5 terms of the sequence h to define the sequence recursively using function notation. So I have to read this because they say h. I'm going to use h of n. All right, so what do I do here? It looks like I am adding 5. Then when I add 5, that doesn't work. So it's not going to be arithmetic. Could it be times 3? I think that works, okay. So times 3. So we're going to take 3 times the term before that. Okay, we have to give the first term. There it is. And then they also like to say n is greater than or equal to 2 because we already know the first term, so we're not going to plug 1 in because we already know that right there. But there we go. We keep on going. We only plug in numbers from 2 on, okay? And really, in all honesty, I don't really like the way that our textbook does this. I would honestly say n is greater than or equal to 2 and a whole number is what I would say. Okay, then it would make a little bit more sense. That way you're not plugging in 2.5 for n or 6.1. You're only plugging in whole numbers greater than or equal to 2. But there is my recursive function. All right.